Hello IB. Today we're looking at 12B3, which is vector equations. So far we've looked at vectors, what they are and how we can describe them. Now let's see about doing some vector equations. We've looked at these a little bit before. So if the vectors form a closed polygon, then a vector equation can be written. In other words, if we've got a whole lot of vectors, we can make them usually into a closed polygon and write an equation. If it's not closed, that means we can't come up with an equal something. The resultant vector will always start at an arrow tail and finish at an arrow head. And that resultant vector closes our polygon, basically. We can start anywhere and make any equivalent equation. So let's see what that all means. Let's say we've got two vectors, in this case r and s. So they might be distance vectors. We're going this direction for r, a certain magnitude and direction. Then we go this direction with s and that distance. The net result is we've gone from here to there. So this is our resultant vector. Our resultant vector always starts where we've started. So that's like our origin. And we finish here at the end. So there's our finish. So we have a double arrowhead at the finish and the double tails at the start. So where there are two tails we start, where there's two arrowheads we can finish. So in other words, we can now say that vector t, our resultant vector, comes from doing r and s. So we've added those two vectors. They could be forces. If we have this force, a magnitude and direction, applying the same force, even though that's acting on the one particle or one body, the net force is this direction. So the physicists can think of forces and what they've done in their physics. In this case, we look at here, we've got three vectors. We've got a vector p going that magnitude and direction, q going that magnitude and direction, r going that magnitude and direction. So we can go, right, where are the two tails together? So we can go, right, oh, here are two tails together, and here are two heads together. So in other words, we can make vector q, not so straight line, vector q can be our resulting vector. So q, that vector, is the same as doing vector p plus, or then doing vector r. All right, so follow that vector, then that vector is the same as doing this vector. Another way we could do this example here is, here we've got vector g, vector f, vector e is going this way and d is going that way. Here are our two vectors starting together with the two tails together, and here are our two heads together. So here we don't actually have one resulting vector that, say, would go from this over to here. We could put that in, but what we can say is that if we did vector g plus vector f, that is the same as, or is equal to, doing vector d plus vector e. That gives us the same result, going effectively from here to here. So we could put that as our resulting vector. Before we go on, I just want to do one little extension here. Let's say, look at this one here. We called q our resulting vector, and we said to get from, shift these out of the road for the moment, if we went p then r, then that would be the same result as just doing q. We could think about, well, if I just wanted to make p my resulting vector, then what I could do, in other words, if I wanted to do a resulting vector of p to q, so in other words, I wanted to write this as, let's put it in green, p is our resulting vector, then how could we get that? How could we make, this is our doubles, here's our starting point with the two tails together. We could go q, but see how this doesn't head us that direction? So what we could do is take this vector but consider it in the opposite direction. So consider this as minus r. So we could do q minus r, in other words, add that opposite vector, and that would get us to the same result as p. And we can see how we're just doing algebra with our vector equations. So q equals p plus r, then we can say p is equal to, and we are just subtracting r from both sides, minus r. So p is equal to q minus r. So same way of doing algebra as we've done before, but doing it with vector equations. So just a little aside there. In this example here, we've got three vectors. We've got an r, an s, and a t, all starting from this original point. Now we want to find the vector rs. So how do we get this vector here, rs, in terms of r and s vectors? So if that's going to be our resulting vector, we want to have, let's shift this out of the road a little bit. We want to make, this is our starting point, because that's what our vector notation says. If it's rs, that's where we start. That's our start. And s is where we finish. So we want those double tails at r. Do we have a double tail here? No, we've got a head and a tail. So if we want to get rs, then we don't want r as it stands. We want to take the opposite of r, so we get tail to tail. So we want minus r plus s, because that would now make tail to head, and we've got the two heads there together. So plus s. So in other words, we want to do that vector plus that one to give us rs. We could also write that as do vector s and then the opposite of r. Is that the same thing? All right. I'm mixing up wiggles and arrows here. All right. Sorry about that. So could I do that same vector if I take, I want to start at this point r. If I do a positive s, remember vectors have magnitude and direction. We are not determining their location. So I can take this vector here. Oops. I want to go green. So here's my vector s, magnitude and direction. And if I want to do that first, I could just bring it over here, join it tail to tail. And now we want to take the opposite of r. Let's go back and draw the opposite of r again. There's our opposite of r. And r now will shift it. And there we have the same story. So this is, let's put some labels on. This is minus r. And this is positive s. So vectors, remember, can be located anywhere. The main thing is they have a magnitude and direction. We'll leave the other two and have a go with those in class. The next section, 12B4, is on geometric scalar multiplication. Sorry about that. In other words, if we want to multiply by a constant. So if we have two vectors that are the same, so here's vector A, we're going this distance, and then this distance again, it's like doing that twice. So when we write 2A, it's meaning double the length, same direction. So that's 2A. This one here, we've got vector A, the same vector, but now we're going opposite direction, and we have three of those. So this vector here, not quite a straight line, sorry, is minus 3A, because it's vector A, 3 times the length, but the minus now says opposite direction. If I want to do half the length, then I've got half vector A. So we can put any constant in front. We can multiply it by a scalar. 3, minus 3, 2, and a half are all scalar numbers. So if A is a vector and K is a scalar, then K times A is also a vector, and we're performing scalar multiplication. We're multiplying by a scalar. If K is positive, then we've got the same direction. If K is negative, we've got opposite direction. And if K is 0, in other words, if we're multiplying by a 0, then we end up with the 0 vector. I just wanted to put one other thing in here. We've multiplied by a scalar. What if we add a scalar? Can we go vector A plus 5? Does that make any sense? Have a think about that, and let's talk about that in class. Here we've got, just want to start off with one of these problems and then we'll finish these in class. Basically, we've got our vectors, R and S, and we want to do some construction geometrically. If you were doing this and you were asked to draw it, you would go, right, well, I want to draw that. It's 2 directions in this X and 3 in that Y direction. And remember those transformations that we talked about earlier? We could write that as 2, 3. So in other words, go 2 in the X direction, 3 plus 3 in the Y direction. What about this one? We want to go 3 in the X direction and then down 2 in the Y, minus 2. So that would be a notation. We're going to use a lot more of that later, but thought we might introduce it now. So if this is our vector R, and I'm just going to draw it in here, 2 in the right, 3 in the Y, so there's vector R. If I want to do minus R, so I'm just doing this one here to start with, minus R, almost a straight line, is now going the opposite. It's now going negative 2 in the X direction. It's made up of that component and then down negative 3 in the Y direction. See, it's the opposite of both. If I wanted to do 2S, let's go red for this one. S is going, I think we can start here. We're going across 3, starting here, across 3 down 2. That's where we want to finish. All right, how am I going to do this? Try and start. I could use it. Oh, forget that. Let's just go to a line here. We'll go this line and we'll go red. So we're starting here. Oh, missed it. Try again. So we want to do a line from here to there. Beautiful. So there's our S. But if we now want to do 2S, we're just going to double that length and go down there and another lot. 3 across, down 2. So they're on top of each other, so it's a bit hard to see. I can shift it. That's exactly the same. Let's shift it down here because it doesn't matter where it is. It's all about the magnitude and direction. So here's our vector S, and this is our 2S. What would be our sort of component version of that? If this is our S and we've now got double that, we've effectively gone 6 in the positive X direction, and we've gone down 4, 1, 2, 3, 4 in the Y direction. So we can see how that works. So let's have a quick go at that one, and then we'll leave the rest to do in class. 2R minus S. So let's go back to blue here. If we want 2R, if I start R here, and where are we going to end up? We were going to have 1, 2, and then minus S is going to go that direction. I need to start right down the bottom. So let's start down here, and we're going to start 2R. We want to go 2R is going to be across 4 and up 6. So we're going to start here and we're going to go across 4. 1, 2, 3, 4, up 6. 1, 2, 3, 4, 5, 6. That's where that's going to finish. Let's quickly draw that one in. So we now put the minus s in, and we saw that before s was plus 3 minus 2, but if we want to do the opposite direction, it becomes minus 3 plus 2. So I've just copied that one and made it opposite direction, so it goes there. So our resulting vector goes tail to tail, head to head. That's that one here. So there's our resulting vector. So in this exercise, we're simply doing some drawing with geometric construction. We're putting component forms in here, which we'll do in more detail later. So we'll have a look at more of those in class. So have a go at those and have a think about this other question that I wanted you to think about. Where is it? Down here. What happens when we add a scalar to a vector? Thanks for listening. We'll see you in class.